Today I will be discussing the concepts of electronic configurations. So it is governed by three rules, Aufbau's principle, the Pauli exclusion principle, and Hund's rule. But today I'll be discussing the Aufbau's principle in this video, and I will also have other videos on the Pauli exclusion principle and Hund's rule separately. But in this video I'll be discussing Aufbau's principle and providing an example. So to get straight into it, Aufbau's principle is a principle where orbitals are filled starting from the lowest energy. So let me drop that down. Orbitals are filled starting from the lowest energy. So what does this mean, per se? Well, this means that electrons will fill the subshells of lower energy orbitals, for example, 1s, before filling the subshells of higher energy, like 2s. So 1s is filled with 2 electrons, so we know that s sub s orbitals can hold up to 2 electrons, p can hold up to 6, d can hold up to 10, and f can hold up to 14 if you didn't know. So this will fill before 2s, and 2s will fill before 2p, and 2p will fill before 3s. So if you're wondering what a subshell is essentially it's made up of orbitals, and an orbital is a mathematical function that describes location and wave-like behavior of an electron in an atom. So if you're wondering what does an electronic configuration look like of a certain element? Well, for example, let's use hydrogen. So hydrogen, we know its atomic number is number 1, and the electronic configuration for this will be 1s1 because it's filling 1 electron at subshell, and the quantum number is 1. And this is S because it's the lower energy orbital that it has to fill. So if you're wondering, what does this S mean? And what does this one over here mean? Well, let me tell you. So this one over here is pretty much referring to how many electrons are in a subshell. So let me just write it down. Number of electrons in a subshell. The S stands for the angular momentum quantum number L. So I will write that down. Angular momentum quantum number L. And this number 1 over here, as you can see, this one refers to the principal quantum number n. So let me write that down. Principal quantum number n. Okay, so if you look at this energy diagram to the left of me here, this is something very useful that is good to take note of when you are constructing electron configurations, because you need to know which orbitals are filled before you fill the higher ones. So for example, when you look at 3p, 3d, and 4s, you're probably thinking, okay, so would 3p fill, then 3d, then 4s? No, it wouldn't go like that. So 3p will fill, then 4s, and then 3d afterwards. So it'll be 3p because you will run into situations like that will fill, then 4s, then 3d. So that is something you have to take note of here. Anyways, like I was saying before, when you're looking at this notation here that I'm moving my cursor around, the principal quantum number pretty much refers to how most of the electrons or most distribution of electrons are from the nucleus. And the higher the quantum number is, the farther it is from the nucleus. And the higher it is in orbitals and atom size. So that's pretty much what it means. The orbitals get bigger, the atom size is bigger as it moves farther from the nucleus, as you increase in quantum numbers. Now, for the angular momentum quantum number, this L over here, as you can see up here, that you see over here. So when you look at S, P, D, and F, this is referring to the shape of the orbital. This angular momentum quantum number L, this is describing the shape of the orbital, which is known as angular distribution. And given the value of this n over here, these n values, L has possible integral values from 0 to n minus 1. So let me drop that down here as well. So L has possible integral values from 0 to n minus 1. So for example, if n were to equal 2, that means that you would have 0 to 1, and this would technically have two integral values. So L would have two integral values from 0 to 1, which is 2. So 0 and 1 are the two values it has that it would have, for example. And the value of n is designated by letters. So like I said before, this L, because it's describing the shape of an orbital, this L here is designated by these letters, as you can see, S, P, D, and F. So L being 0 is S, L being 1 is P, L being 2 is D, and L3 is F. So that is kind of the background I just want to give to what this notation means, if you're wondering. Now, let's jump to a few examples, shall we? So I'm going to put some examples here. So now one thing I want to note is that you want to make sure you have your periodic table on hand here, so that way you know what atomic number is what when you're asked, and I'm sure you will be giving this on your exams because this is important to know. Let's do something simple. Let's do oxygen. So oxygen, you can go down here. I know it has an atomic number of 8. So 8, okay. So atomic number is 8, right? So oxygen has 8 electrons. Now we're going to fill these electrons using Aufbau's principle. So let me just move this up. So this is Aufbau's principle. And so what does this mean? Orbitals are filled starting from the lowest energy. So one thing I want you to note and keep in mind is that S, this is something that you have to know because it's very important. So S can hold 2 electrons, P can hold 6 electrons, D can hold 10 electrons, and F can hold 14 electrons. So this is something that you have to keep in mind when you're filling these orbitals. So now that you know that, we're going to start from the lowest energy orbital. So these are lower energy orbitals here. So this is the lower energy orbital we're going to fill first. And since S holds 2 electrons, we're going to say, and we know that this has its atomic numbers 8, so that means oxygen has 8 electrons, right? So that means that we're going to fill 1s, 2. We're going to have this be filled to 2 electrons because it can hold up to 2 electrons. So this is a lower energy. This is a lower energy orbital here, as you can see. So this is filled. Now we're going to move to 2. So this is a higher energy orbital compared to 1s. So this 2s will be filled and it will hold another 2 electrons. Now, since we filled 2s, we're going to fill 2p because now we filled this and we're going to fill 2p now. And 2p can hold up to 6 electrons. So this is already, we have 2 and 2. We're going to fill, we need another 4. So that means it'll be 2p4, as you can see here. So this is one example of an electron configuration of oxygen. And that's what you would write in your exam. So the ground state electronic configuration of oxygen is 1s2, 2s2, 2p4. So let me just write that here. Ground state electronic configuration. I can't fit that whole word, so I'll just write this. All right, so another example that I will do is, so sulfur has an atomic number of, as you can see, 16. So it can hold up to 16 electrons. So using Aufbau's principle, like we know already, we know that it's going to fill 1s, 2s, and 2p. So we're going to follow this diagram here. So it's going to be filled 1, 2, 3. We're going to follow it. So first it's going to fill 1s2. All right, so now we have 14 more electrons to fill up. Then it's going to fill 2s2. 2s2. Then it's going to fill the 2p orbital here. Now, like I said before, the p can hold up to 6 electrons. So that means it'll be 2p6. Now we have 10, so we need 6 more. All right. Now it's going to jump to 3, this quantum number. So n equals 3, it's going to jump to this higher orbital here. So 3s2, it will fill up. 3s2. So now we have 2, 4, 6, 6, 6. So now we have 12. Now we have 4 more electrons that we need to fill up. So that means that we're going to go to the p orbital now. Now that we filled the 3s, now we're going to go to the 3p orbital. So this 3p orbital will be filled. So what's remaining left? And we know that p orbitals can hold up to 6 electrons. So that being said, it's going to be now 1s2, 2, 4, 6, 6, 6 is 12, 12. So this is going to fill up to 4 electrons. So that fulfills it. And I'm going to box this. Oops. So the ground state electron configuration of sulfur is 1s2, 2s2, 2p6, 3s2, and 3p4. Ground state electronic configuration. Now, I said in the beginning of this video that I will be discussing Hund's rule and the Paul exclusion principle, and I will, and I'm going to discuss it using these two examples here in terms of building energy level diagrams. So when you're building ground state electronic configurations, you're going to take into account Aufbau's principle because you are filling orbitals starting from the lowest energy. So 1s is going to be filled before 2s, 2s will be filled before 2p. And when you're taking into account those other two rules, that is pertaining to filling energy level diagrams that you would have to illustrate out. And so in the next 2 videos, I will be showing that. So stay tuned. So I hope this helped you out, and the other ones will be posted very soon. So here is the ground state electronic configurations of oxygen and sulfur.